Last hour. So they probably did get it fixed.
Okay.
So for those like Lee and everybody, we should be able to get it there. And that way Kyle can join in because he'll be able to speak up. Class would probably be just a little on the short side today. Well, I woke up in the middle of the night and realized I hadn't really wrote out my notes for today. So now I have notes and I have problems, so it's good, so that's where we are at. And then given the technical difficulties that I've had this morning, I'm a little exasperated. Every time we switched, we had the class work part-time over there, and then it would go black screen. And then it would come back, and it would go black screen. So things were not peachy dandy. So you guys should have all been able to access your Mastering Pearson book, hopefully getting in. If you are having difficulty with time delay or anything like that, please contact tech support, because the problem that Kayla and Corbin were telling me about, that it was like having a delay adding or bringing a screenshot or something like that, please, please, please contact tech support, because I don't think that's something on our end. I think it's something on their end. So my recommendation is to print out your homework to start with, because these things, all of statics and dynamics, so as you get up to dynamics, it's all about drawing your pictures and trying to keep your pictures straight. So, and looking at it from that perspective. So those are the things that we're dealing with. And so, remember what this time it's really, I don't want to do that because that will mess up my paper. We are all about looking at the two fundamental things. The summation of forces equals 0, which means that my acceleration is going to be 0. And we're going to talk about the sum of the moments, which is related to torque, has got to be 0, and that relates to my moment of inertia and my angular acceleration. So these are our two conditions of equilibrium. And that's where, make sure we're recording. Those are my two conditions of equilibrium, and that's what we're going to be working with. So the first chapter was all about doing conversions, looking at our SI units. We are going to use, remember, for acceleration due to gravity, we are going to use 9.81 meters per second squared, and we're going to use 32.2 feet per second squared. And that's because we're going to deal with weights, and weights are going to be mass times gravity. Our common units that we're going to have are newtons for forces, for SI, and pounds for my common units. And you will also see pounds written like this. And later on, as we get into certain things, you'll also see another set of units that'll come up when we're talking about massive amounts of things. Okay, so the first chapter is pretty much just that basic review, and then we start really getting into stuff in our second chapter. And that's what we're going to start with today. All right, so it's all about the vectors. Okay, everything's all about the vectors. So one of the things, we're going to use something that's a little different than what we did in general physics. We're going to use a fundamental principle called the parallelogram law of forces. Now we know that if I have a vector and I want to deal with my vector, I can add my vectors head to tail, right? Hopefully I beat that into you in Engineering Physics 1 over and over again. And then if I didn't beat it into you enough then, we did it when we started dealing electrostatics and electric fields and everything else. We beat in vectors or head to tail. Now, one of the things that we're going to use a lot, okay, is if I have a vector, I can represent that vector as AXI plus AYJ plus AZ in the K direction. I can also represent this vector as A, and then I have a little thing called the unit vector. Okay? And my unit vector is essentially I plus J plus K, because each one of those has a magnitude of 1, right? And it's a unit vector in each of those directions. So if I'm actually drawing that unit vector, so if I've got my lovely handy dandy grid paper, my unit vector, here's my I and J if I'm in 2 dimensions, and then I've got my K in my 3rd dimension. And I still haven't gotten you your isometric paper yet. Okay? But you will want to get isometric paper because it's going to help you out a bunch. Because essentially, eventually when we deal with 3 dimensions, so if I have my system here, so this is my X, Y, and Z, my unit vector is going to come out, I'll do it in green, it's going to come out, here's my unit vector, here's my unit vector, and then here's my unit vector, and then my actual vector, if I do a black, is going to be from here to here. So what you're going to end up with, so if we have a vector, I'm going to have my component in the Z direction, so this is AZ. I'm going to have my component in the X direction, or this is my vector AYX, but I can have this right here. This is going to be AY, and this part is AX. So if we remember it from good old somewhere in math class along the way, right? This vector here is the projection of our vector A in the XY plane, right? Everybody kind of remember that along the way? And we've got a projection, which also means that we're going to see angles here. So here's an angle, this is an angle, and that's an angle. So we're going to get these angular things when we start working in 3 dimensions. So we're going to have those pieces that are out there. But like I said, we're going to deal with what we call the parallelogram law of forces. Because remember, I can shift vectors around, right? I can shift vectors around. So get my handy dandy paper towel so I can wipe this off. Okay, because I can add head to tail a couple different ways, right? I can add head to tail a couple different ways. So what ends up with, if I'm adding, so this is this same vector, and this is that same vector. I've just done it in a different place. The resultant vector that we get this is our R vector. It doesn't matter which way I have it, I have a parallelogram. And sometimes that parallelogram is going to help you out a lot, okay? Sometimes that parallelogram is going to help you out a lot. Sometimes working with the parallelogram is going to be the easier way to deal with something. Other times, doing our traditional adding our vectors, A vector plus B vector is going to give me my C vector, is going to give us that piece. So, you know, we've seen this problem before because we started with this problem. I have my little boat here, right? And I've got the mule over here pulling with a force, and we're going to use that force as 60 kilonewtons. And I've got another force over here, and we're going to use that force as 145 kilonewtons. And we're told that this angle is 25 degrees, and we're told that this angle is 30 degrees. We want to know the resultant force. Right? We want to know the resultant force. Well, I can do this geometrically, because I can put my 60 kilonewton force here at 25 degrees. And that is going to give me some resultant vector. If I have drawn this to scale, that looks like that. Guess what? That's my parallelogram. Okay? It's my parallelogram because I could have slid this vector up here to come down there. I could have done the same thing. And that's 30 degrees. So I could have done it just the same way. And if we did it the old longhand way, right? So we can do it the old longhand way. Drink so I don't spill my drink. We got our picture there. I can take force 1. Force 1 is going to be, and we're going to use force 1 to be the 145 kilonewtons, so it's 145 kilonewtons. Cosine of 30 degrees in the I direction, minus, because I'm in the negative y, I got 145 sine of 30 degrees in the j direction, and that's going to give me, if I plug that into the calculator, 125.6 I minus 72.5 j. I can do the same thing for vector number 2. That's 60 kilonewtons cosine 25 degrees I plus 60 sine 25 degrees j. It's going to give me my 54.4 I plus 25.4 j. Add those two together because this is going to be F1 plus F2. It's going to give me 180 I minus 47.1 j. We know that the resultant, because we've done these how many times? 180 squared plus 47.1 squared. That's going to end up giving me 186 kilonewtons. And I can do my angle, which is going to be the arc tangent of minus 47.1 divided by my 180. And it ultimately gives us 14.7 degrees below the horizontal. So if I did this over here on my picture, this angle is 14.7 degrees. So all good? Does this look all familiar?
Will you scroll it down a little bit?
Which one? This one?
Yeah.
Look familiar?
Decently.
Okay, we'll do a little bit of expansion. A little bit change up here. We're going to do the similar thing with the boat. So I got my little boat here. This time we know that the resultant force has a magnitude of 115 kilonewtons. We know that this force, one of the forces is 80 kilonewtons, and it has a 35-degree angle. We don't know the force there, and we don't know that angle. And that angle is not from the horizontal, that angle is from the resultant force. Well, actually, that's not true, because this vector, I'm lying to you. This resultant force is actually given to us as 115 kilonewtons strictly in the I direction. So we actually did have more information. My apologies. So we can approach this a couple of different ways. The way I'm going to approach it is that the resultant force is 115 kilonewtons in the I direction. We know force 1 is 80 cosine 35, and we know that this is 80 sine 35. We know that force 2 is going to be Fxi plus Fyj. Now, what's going to be needing to know is that my x and my y directions are independent, right? We know that they're independent. So Fy plus 80 sine of 35 has got to equal 0. Because there is no y component in my resultant vector. So that's got to equal 0. So Fy has got to equal negative 80 sine 35, which should be 45.9, negative 45.9. And this is going to be in kilonewtons. And then Fx plus 80 cosine 35 has got to equal 115. So Fx is going to equal, this works out to be 65.5. So that's going to work out to be 49.5, if I've done that right. Which means the tangent of my angle has got to equal 45.9 divided by 49.5, which is going to be a 0.927, and it gives me alpha is equal to 42.8 degrees.
We make this seem easier than the homework.
Well, the homework throws in three vectors, right?
Not yet on the. I've just been doing it with the law of cosines and sines.
Well, you can do it that way too.
And this way it seems much easier.
You can do it that way too. I mean, that's one of the things that's out there for you. You can do it that way. Yeah, and once you've got that parallelogram, and see, that's why we talk about that parallelogram, so let's look at that again. Okay, everybody get this? I'm about to erase it all. So let's look at that particular situation that I just had, right? So if I have, this is the 80, right? This is the 115. And this was our unknown. Well, we know that this side is not drawn to scale, right? This side becomes an 80. Well, if I want to find that angle, I can use my law of cosines. Because my law of cosines says, if I have that parallelogram, right? If I have a triangle, and I need that one, but I have this side's 115, that side's 80. This is going to be B. So B squared is equal to A squared plus C squared minus 2BC cosine of the angle. AC, sorry, AC. So if I have any two pieces of information, I should be able to get the rest of it. Because if I look at this, this is going to be, we're going to make this A, this is little a, we make this B, that's little b, we make that C, that's little c, and I have any one of those, I can actually utilize it. In fact, cosine of, if I take my different ones, the cosine of the angle is equal to minus A squared plus B squared plus C squared divided by 2BC. And then you can go through cosine of beta is equal to A squared minus B squared plus C squared 2AC. Cosine gamma is A squared plus B squared minus C squared divided by 2AC. So you can manipulate this to get you your law of sines and cosine. So that's another way to do it. And that's what you guys are going to find, is there's more than one way to do these problems. More than one way to do them. Because the other thing that we're using here that's helping us out is the thing that we call the principle of transmissibility. All right, get ready. The conditions of equilibrium remain unchanged if a force acting at a given point of the rigid body is replaced by a force of the same magnitude and same direction acting at a different point. Provided that the point, and this is the critical part, provided that the two forces have the same line of action. So I can move my force, what that's telling me is I can move my force around.
But as long as there's something to cancel it out.
Well, I can move, well, it's provided that it has the same line of action, okay? So, for example, best way to do it, you're right, it's something that's canceling it out, but the principle of transmittability is not just for statics, okay? In this case, we're talking about having something to cancel it out. This is not just for statics, it's also for dynamics when we get to dynamics as well. But what that's saying, essentially, is this. Well, let's actually do it with a physical object. Okay. Even in dynamics, if we're doing in one dimension, so if we look at it in terms of one dimension, it's easy to see. If I have a force that is applying to my calculator, and I'm going to apply the force that way, and we know that the calculator is going to move that way, right? I can apply the force that way. Now, because I'm only dealing with one dimension, principle of transmissibility says it doesn't have to be applied directly right there. I can apply it right here because I'm only dealing with one dimension, okay? I can apply it over here and I'm still okay, it's only in one dimension. Now, if I have to worry about two dimensions, okay, so I'm going to put my finger here and I'm worrying about two dimensions, the principle is not going to allow me if I'm going to push and it's going to allow it to rotate, all right? Now, because I'm in equilibrium, it doesn't matter, right? This is going to be a resistive force, and this is a resistive force, and I can move that force around. But later on, when we get to dynamics, I may not be able to do that. But if we're looking at this, okay, for example, in dynamics, I can apply this force anywhere along here and have it still move here because I am not above that lever arm to cause it to twist if I'm in a certain situation for shear or something like that down the road. So I can use this principle later on. It's not just for statics. The key is, you know, as long as I'm pushing along this way or anywhere along this way, then I'm, you know, as long as I can move it and the forces that I'm trying to deal with are in the same line of action, I'm all right. What that's letting us do is if I go back to my triangle or my parallelogram, so I got my parallelogram here, that's saying that I can move this force up and down this line without causing a problem. Allow me to add it head to tail. Is that making sense?
So long as it's the same magnitude and direction.
As long as it's the same magnitude and direction. So long as it's the same magnitude and direction. And that's why you can start doing some weird things. Like if we know that this is 25 degrees, right? We know that's 25 degrees. We know that side and we know this side. So this is an A side and this is a B side. We can figure out what that angle is, right? Which means we know that angle. So when we draw our pictures, we can get a whole lot of different information. We can get a whole lot of different information. But so that principle of transmissibility allows me to slide my forces around. It allows me to move those forces around. Okay. Okay, I'm gonna draw a picture. I don't have the actual picture with me. I thought I did, but I don't. It's all right, I walked into Physics 2 today with my Physics 1 notes. So luckily it was first day of Physics 2, so it's okay, you know, but still, you know, the semester's starting off nice, So, so I don't have the overall picture. And usually what I'm going to do for you guys so that you guys can see it is this is one thing that I generally will do when we work a problem is I will actually print out the picture that's provided with the problem so that we have a big picture of it. My notes, I have the solution, but I don't have the original picture. I will tell you, I think it's problem 220. I'm not 100% sure, but I have the original diagram, okay? I have the original diagram because we're ultimately going to want to draw the resultant force. So I've got, but usually what I'll end up doing is giving you the picture so that you have it and referring you to where it is in the book. So the picture gives me something like this. I've got a vector Q. I have a reference point here. I have a line here. This is listed as 25 degrees. This is listed as 55 degrees. And then I have a vector P over here. And that vector is listed at 85 degrees from this reference line. And P has a magnitude of 60 newtons, and Q has a magnitude of 48 newtons.
I think the picture was just shifted to the,
It may be. I just don't remember. I just don't remember. I don't have my actual picture that the problem's coming from. But this is. I think it's problem 220. So what we end up with. So I can redraw this situation. Okay, I can redraw this situation because we're going to add P and Q. That's what we're doing. We're going to find the resultant vector, which is going to equal the vector P plus the vector Q. And so I can redraw this because I can use my principles here. I've got my vector Q, and my vector Q is at 80 degrees, and I'm exaggerating things a little bit. And we're going to move our vector P, so it's adding here. And if I do these lovely calculations, I find out that that is 110 degrees. So my resultant vector looks like this. Okay? My resultant vector looks like that. And you can utilize, so now if you draw it like that, you can utilize the law of sines and cosines to get what you need because you can redraw a few things that happen. But we can also do it the old-fashioned way, and we say that P is equal to P cosine the angle I plus P sine of the angle J. And that, if we do that, gives me 60 and 25 plus cosine of 25 plus 85 I plus 60 sine of my lovely 110, right? 25 plus 85 is 110. J is going to give me P is negative 20.5 newtons in the I direction and 56.4 in the J direction. Now, things that are going to trip you up. When you're looking at this, make sure these are reasonable. P is in the second quadrant. If this is quadrant 1, this is quadrant 2. So make sure, so you've got your alignments in there. And that's one of the things as we start moving the triangles around, you're going to want to keep track to make sure that your directions are correct, because depending on what information I have, I may be using this and I end up with a positive answer, but I want to make sure I'm in the right quadrant and it's pointed the right direction. So you want to kind of keep track of that and keep looking at that. And I can do Q, and Q is going to give me 48 cosine of 80 plus 48, and that's in the I direction, 48 sine of 80 in the J direction, and Q ends up giving me 8.34I plus 47.3J. And so my resultant vector ends up being negative 12.2I plus 103.7J. And the magnitude gives me 104.4 newtons. And then my angle, if I do my angle and I do the 103.7 divided by my 12.2, that's going to give me 8.5. I think that's right. Oh yeah, that gives me 8.5 when I do that. And it gives me my angle ends up being 83 degrees. And the trick is figuring out what that angle is. That happens to be this angle. Okay? So you gotta keep track of where the angle that you're calculating is based on how you do your calculation. But here comes the tricky part. Mastering may be asking you for this angle. Okay, so I've calculated that angle, and if I plug that into mastering, mastering may go, eh. Mastering may be asking you for that angle. Or it may be asking you for this angle up here. Or it may be asking you for that angle right there. So you've got to be careful when you're working the problems to make sure that you know what angle it's asking you for.
And it uses a bunch of big words.
And they use a bunch of big words.
It uses a bunch of big words.
It may be asking you for the complementary or the,
Supplementary.
the supplemental angle, or, so you got to kind of go back and look at it. So don't make it harder than it is. That's the first thing. Don't make it harder than it is.
Counterclockwise from the X.
And that's the other thing. It will also say counterclockwise from the X or clockwise from the X. It will. Those are definitely things it will offer you. It will actually tell you.
It's a little neat.
It's just, depends on what you're trying to do. And actually part of it depends on what you're trying to do in your miter saw. So, I mean, that's kind of why we end up with it. All right, I'm going to stop there. I'm not going to challenge technology any more than that. Thank you, Robin.